All right, very good. So now let me just say something that I want to share with you. When I was studying AP Chemistry, this is the unit that I just missed before I joined AP Chemistry back then, since I joined after this unit. So I had this self-study of this. Now, let me tell you a few things that I had no idea back in the days. I was looking at all these four graphs, and I'd be like, what are these graphs? And I couldn't even grasp the simplest understanding that is, well, you have reactants, right? Well, what's going to happen to the reactants concentration? It's going to drop, right? It's common sense. And that to me at that time, it wasn't common sense. And then what about the products? Well, at the beginning of the reaction, there wouldn't be any products, but as the reaction progresses, there will be more products. And I was like, oh, yes. So what you described was very well. So the two reactants, B will be Q and D will be P because they are what? They are the concentration is decreasing and D is definitely P. It's because there's a coefficient of 2 right here. That means the consumption rate, it's going to be twice as much as Q. So that's why P should have a much faster drop in concentration. For the reactants, A is going to be R and C is going to be S for the same reason. The concentration shall go up over time. And since there's a coefficient of 2 in front of R, then the production of R should be pretty high. All right, now let me tell you another thing that freaked me out back in the days. I was like, hey, how come there's a disappearance of P and sometimes you will see appearance of R and S? It freaked me out because I was like, wait, hold on, how am I supposed to know disappearance or appearance? Well, if you are dealing with a reactant, what's the fate of a reactant? It would decrease, it would disappear. And I was like, oh, that's a reason. And for us, now, what should be included right here, it should say what's the average rate of disappearance. Okay, that is, it started with 1 molar, and then it goes down to 0.4 molar, and then and over 20 seconds. So the calculation would be 1 minus 0.4, which is 0.6 molar divided by 20 seconds, and so 0.6 divided by 20, it's going to be 0.03 molar per second. Okay? 0.03 molar per second. Now, before I move on to the next part, I just want to make sure that you are very well aware of this based on your entire unit's understanding. First, this is just the average speed, the average rate. Will the rates be different afterwards? Well, if you look at the graph right here, seems like it's going to be different. The slopes are changing, okay? But just one thing that you need to know is that when you need to make any sort of comments about the rate in the future, you must ask yourself, do we have any information about the order? Like, is it zero order, first order, or second order? Okay? You can't just say, oh, it's 0.03, it's going to keep going 0.03. Well, that it's only true if it is zero order. Okay. What about disappearance of Q? Well, if P drops by 0.6, so the way you can talk about the way you can do this, it's that you can do this. It is simply a stoichiometry because they are in mole ratio. So we can say, hey, the rate of consumption of Q should be half as much as P because it's 2-to-1 ratio. So that's why you divide by 2. What's the concentration of Q after 20 seconds? All right, now, so this it's really about your holistic understanding. Okay, so for P, it dropped by 0.6 molar. So in 20 seconds. So for Q, how much should it drop if the ratio is 2-to-1? 0.3 molar. Does it make sense? If P drops its concentration by 0.6 molar in the first 20 seconds, then Q must drop by 0.3. 2-to-1 ratio. 2-to-1 ratio. So they all start with 1 molar, so the concentration remaining after 20 seconds would be 1 minus 0.3, which is 0.7 molar. Okay? Now, I can foresee some problem with these questions for part C in particular, and that is some students will be like, oh, let me go ahead and use the 0.4 molar and do the mole ratio. And they forgot about the whole process, that the way you calculate the concentration of Q remaining is by knowing how much it has been consumed in the process, in the 20 seconds. If P consumed 0.6, then Q must have been consumed by 0.3. What about D? What's the concentration of R and S after 20 seconds? Now, this is why I laid out the statistics right here. If you understand how P dropped by 0.6 and Q dropped by 0.3, so, well, why they are dropping? Well, they are dropping simply because they are making products. Therefore, R concentration must be 0.6. Because its ratio, it's the same as P. The mole ratio, it's the same as P, 2-to-2. So if P dropped by 0.6, well, then R must go up by 0.6. And S must go up by 0.3 molar. And just a little sneak preview of second semester. We are doing a whole lot of concentration calculations like this in the second semester. Okay, so just buckle up. So if I have to label one part of the question that you need to be careful for, I probably will label part C. Just make sure that you are thinking reasonably. You are not just diving in and say, all right, which number do I pick? As you can see, this number, it's not part of the question. This number, it's not explicitly stated. You have to understand it and extract that number out from the text, out from the data.